Hi everybody. Sorry about the delay there. I had everything all set up and I'm like, why isn't there anybody in the chat or even like viewing? And then I realized I had connected to the wrong account and I didn't know if it was sending it to the right spot. 'Cause YouTube doesn't tell me that. I had this little like joke all set up about like, what are you doing here when it's so beautiful outside? And then it suddenly started pouring. So, so much for that, I guess. So instead, let's do some chemistry. Welcome back to Chem 140. Today we are going to cover Unit 15. It is one of the last 2 units of the chapter. As soon as I started talking, here comes Maya. Maya wants to say hi. Here you go, say hi. Yeah, they're gonna do chemistry. She is the chemistry cat. What do we have on the agenda here? So quiz 6 closed last night, it looks like. Quiz number 7 is due tomorrow. Lab worksheet number 5 will be due next week. I gave you extra time to do that for reasons, question mark? I don't know. Maybe you needed it. It's just what the syllabus said, so I was stuck with that. Yeah, that's really all I can think of. Oh my goodness, hold on, I had to deal with a cat. Where are you? Squirt bottle. Stop. Stop. Yeah, I can't teach with just this cat at my feet going meow, 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 meow. Alright, so yesterday we went over, or not yesterday, sorry, but the day before, we went over balancing chemical equations. We're going to use those equations to determine quantities in specific reactions. Now, this is kind of the whole meat and potatoes of 140. Like, if you can make it here, you can make it anywhere in 140. This and Unit 16 are just like the capstone. We're going to take everything we've learned in this class and put it all together. All right, so here we go. I'm going to take this reaction, as shown. 4 ammonia and 5 oxygen makes 4 NO and 6 H2O. And we're going to make some statements relating the molecules in this specific reaction as written together. So, for instance, I could write, I've already written it right here, but I could write it like this. So, 4 molecules, NH3, would react to make 4 molecules of NO. They make other stuff, but this relationship is true and we're looking at just those 2 things. Or I could write, I use 4 molecules of NH3 and that also requires 5 molecules of O2. So I'm comparing the 2 reactants here, for example. Or I could compare the products. I could say, for every 4 molecules of NO I make, I also make 6 molecules of H2O. How am I getting these statements? I'm basically just choosing any 2 and writing out what the equation means. Now, we don't work with molecules very often. Instead, what we work with are... Oh, my L didn't stick around. We work with moles, right? So, if I multiply both sides by 1 mole, I will get a relationship that uses these coefficients. So, these numbers right here. I can relate any 2 together. I just have to put the number in front of the reactant or product in my ratio. So that would be for relating NH3 and NO together. And I could do the same thing for any of the 2, any pair that I wanted to. Since there are 4 different things, I could compare ammonia to each of the 3 other things. Compare oxygen to the other two, and then NO to water, which is left over. All of these relationships are valid for, specifically, this reaction is written. If I change the reaction, then I have to change the relationship. So these are not absolute truths, but relative truths to the problem that we are exploring. So that's why when you look at this, you might be thinking, oh, wait a second, H can't equal O. Like, those aren't the same at all. But within the context of this equation, that statement is true. There are other facts that we are omitting because we just don't need to look at 4 things at once. We can pick any 2 we want. So what does that mean for us? Well, if I know the number of moles of something, I could convert that to the moles of something else. And if I know the number of moles of something, I can convert that to the number of grams of that something. So this is called stoichiometry. And so the whole point of Unit 15 is for us to learn how to do chemical calculations of the exact same nature that we were doing when I gave you a problem that was similar to, I give you 500 milligrams of aspirin. How many milligrams of that is nitrogen? I think the answer to that is actually 0. I should have said oxygen, but that's okay. But using the formula for aspirin, you could then say, oh, in 1 molecule of aspirin, there are this many oxygen atoms. Therefore, in 1 mole of aspirin, there are this many moles of oxygen. Same thing is going on here. We're going to do those types of calculations for today. I just threw the pen on the floor. All right. There we go. So let's suppose that I have 16 moles of ammonia in the flask, and I have all the oxygen that I need. I'm not going to run out. How many moles of water would be made? So what we would do is we would say, okay, this is the unit I'm starting with. And I want to figure out moles of H2O. So what relationship do I know that relates these two things together? Well, I know that for every 4 ammonia I put in, I get 6 water out, right? So I could say for every 4 moles of ammonia that go in there, I get 6 moles of H2O out. And I accidentally messed up with my pen there. So I can set up my units like this. Moles of ammonia, which will cancel out. Moles of H2O. And that'll give me an answer in moles of H2O, which is what the problem wants. Now I just gotta fill in the numbers. There were 6 H2O and 4 ammonia. So I do the math. 16 times 6 divided by 4. What is that? That looks like 24. So that's how we would do a basic mole-to-mole calculation for this type of problem. So now what I want you to try and do is, let's do the same thing. If I use 25 moles of ammonia, how many moles of O2 are used? Do the mole-to-mole ratio and do the calculation. We'll go over the answer in about 2 minutes. I'll see you in a bit. Once you have an answer, type it in the chat for me. All right, let's go over the answer here. All right, so I want to go from moles of ammonia to moles of oxygen. And the relationship that I have there is not on the screen anymore. So let's go back. So it's 4 moles of NH3 is equal to 5 moles of oxygen. So I had to have that on the screen so that I could look at it. All right, and we have 25.0 moles of NH3. So I'll set up my units. Oops, hold on. So that the moles of NH3 cancel out, leaving me with just moles of O2. And so now we just run the numbers. So there were 5 O2 and 4 NH3. So whatever 125 divided by 4 is, 25 times 5, 31.25, which rounds to 3 sig figs, 31.3 moles of O2, which is what y'all got, so that's great. All right, now that you know how to turn things from moles of something to moles of something else, you could then turn those quantities into grams. So if instead of moles, I wanted you to tell me what mass of oxygen you had, or maybe instead of giving you moles to start, we gave you a mass of ammonia to start with, you could do this calculation anyway. You just need to do the extra step. So you would convert from grams to moles, then do this mole to mole ratio that we just did, and then do moles to grams. So that's where we're going with this for today's lecture. All right, I'm going to give you an unbalanced equation, and then I want you to answer these questions about it. So fill in the blanks, balance the equation, and then if you have 24 moles of glucose and all the oxygen ever, how many moles of CO2 would be made? And then if you made if you did a separate reaction and you created 180 moles of water, how many moles of oxygen did you also need? Okay, so go over these answers. Type your answers in the chat when you got them. And then we'll go over them together as a class in just a little bit. I can see it registering on my mic here. So not only are there people leaf blowing outside in the pouring rain, the apartment next to mine is being renovated. So I apologize for any construction and or landscaping that you hear in the background when I'm talking. How are we doing? We got the equation balanced. 1 or 2 more minutes should be okay. Yeah, go ahead and keep working. All right, let's go over the answers. I gotta clear that. Oh, that's not great. Hold on. I went and erased everything, and then this happened. Oops. Oh, that's not what I wanted to do either. Gonna delete my scene on accident. Oh, there we go. That time it worked. How odd. So first we gotta balance the equation. So we got we have the combustion of glucose. This is what your cells do. They consume glucose for energy. And since there's a 6 for carbon here, this makes sense to do. And since there's a 6 or a 12 for hydrogen here, makes sense to do that. So now we have 6 carbon and 12 hydrogen on both sides. All I have to deal with is oxygen. So I need to have a total of 6 times 2 is 12, plus 6 is 18. So if I can put something here that would give me 18 total oxygen, minus these 6, so 12 total oxygen. There we go. That's what my brain does when I'm balancing these equations. I know somebody said the other day, like, wow, you balance equations really quickly. And that's what I do, is I look at where things are going. So you could totally do the inventory and just do this and count everything up, and that's fine. All right, now we got to do the calculations. So the first one is if I had 24 moles of glucose and excess oxygen, so I don't run out of oxygen doing this, how many moles of CO2 would I make? That's the eraser, and I don't know why it's stuck on it. There we go. So to go from moles of glucose to moles of CO2, we would just use this ratio. So 1 mole of glucose is equal to 6 moles of CO2. And so we'll do the calculation. So if I have 24 moles of glucose, I can convert glucose to CO2, cancel them out like that. That'll give me moles of CO2 for my answer. And then we just run the numbers, right? So 6 CO2s, there we go, 1 glucose. So whatever 24 times 6 is that 144? Yeah, it's 144. There you go. And then for the second question, what is that, 180 moles of water? Yeah. I have moles of H2O, and I want to figure out how many moles of oxygen are needed to create this much if I have sufficient other stuff. So using the equation that we balanced out, I could find out that for every 6 moles of H2O I need 6 moles of O2. Well, if every mole of H2O makes every mole of O2, I should just get the same answer, right? Well, let's show that that's the case. So if I have 180.0 moles of H2O, oops, I can do this dimensional analysis to get my moles of O2. And then I would just put numbers right like this, right? So there's 6 for each of them. And when you divide something by itself, it just cancels out, yeah? And that's all you need to do. So that's how you do those calculations. All right, any questions, let me know. All right, so when we were talking about the law of conservation of mass earlier, and we said how we had to balance both sides of the equation in order for us not to be creating or destroying mass, when we do reactions, the law of conservation of mass still applies, and you can see it in the math that we're doing. So for instance, if I was able to turn the number of moles on both sides of the equation into masses, which is not difficult to do if we know the molar mass, you can go to LenTech to do that, to get that molar mass number. You can see that the equation will be properly balanced. So let's look at an example here. So what I'm going to do is I'm going to say, okay, if I have 4 moles of this and 5 moles of this one, and 4, we'll put an equal here, 4 moles of that, and 6 moles of water, if I made each of these a mass, and then I added them all together, we can see what our totals would be. So let's do that really quickly. So if I go to LenTech to get the molar mass calculator, I type in NH3, so 4 moles NH3. And according to Lentech, I could convert moles of NH3 to grams of NH3, and the number of grams in that quantity is 17.03. And so that would be 68.12. So that's this one. Then I could do this for oxygen. We'll do the same thing. Ah. Sorry. So 5 moles times 32 grams per mole is 160.0 grams. So that's the mass of the left side, would be those two things. And if we add those together, we would get that many grams. Okay, let's rearrange all of our stuff to get these two compounds. Then we'll do the same calculation over here. So 4 moles NO. And I don't know what that is. I think it's 30, but we'll check. 30.01. So that is 120.04 grams per mole. We don't get to keep that 4. And I can do the same thing with my H2O. Those cancel out. And I get 108.12 grams of H2O. And I can add those together. 120 plus 108.1. I get 228.1 grams. And would you look at that? So the law of conservation of mass applies not just in the counting, but also in the mass, because we have massed all of these atoms, and we've taken that into consideration on the periodic table. So the numbers that you are using from the periodic table will have that already factored in. All right, so I'm going to hit clear, and then the slide will do all of that calculation that we just did. Mine was off a little bit, probably due to a different periodic table I was using or something like that. But we can verify the conservation of mass very easily by looking at any balanced equation. And that also highlights the need for your equation to be balanced, because if any of those numbers was different, we wouldn't have the correct numbers on both sides. We would have something that was very different. All right, let me check the clock real quick. Oh, we have time to start this. All right, so let's put all of that together with being able to convert from grams to moles and do some actual problems that you would do in a laboratory. All right, so if you can turn moles of something into moles of something else, you could take each of those moles and turn them into grams or particles or whatever. And so this is called stoichiometry. So we're going to be doing problems using this chart again, because the chart we're doing the same type of problem. It's just that to go from moles of A to moles of B, you use the coefficients in the balanced equation. So let's do an example using sodium azide here. So sodium azide is used in your car. And the way this works is that, so let's suppose that this is your car. Everybody has a Jeep like me. So, and I'm just going to draw the front of it. So there's your wheel. And here's the steering column. And if you bonk something with your fender, what ends up happening is the fender is connected to a circuit which contains your sodium azide. Somewhere along that. It's basically triggering a fuse, and when the fuse lights, the sodium azide decomposes into sodium and nitrogen gas. And so this is all connected. So then this area fills with nitrogen gas really, 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 really quickly. And it goes out the steering column, which then inflates the airbag very quickly. If you've ever had your airbag go off, you can see how fast this reaction occurs. Like, the airbag is almost instant, just thump, and then suddenly there's 70 liters of nitrogen in your face. All right, so that's how airbags work, and they work using this chemical reaction because sodium azide is really good at decomposing very quickly. And so here's the balanced equation for that. So what we want to do for this specific example here is I'm going to put 20 grams of sodium azide into a reaction vessel just as a test reaction to see how much nitrogen I generate. What mass of nitrogen is formed? So let's do this problem together. And then I'll have you do the next one. Oh, Photoshop. There we go. All right. So I want to start with a mass. So the first step that we're going to do is we're just going to turn both of these into moles. So moles, sodium azide, and moles, N2. And then finally, we'll link these together using the mole-to-mole ratio in the equation. What is that mole-to-mole ratio? So for every 2 moles of NaN3, using the balanced equation up there, I make 3 moles of N2. And then for these other relationships, it's just going to be 1 mole of whatever is how many grams according to Lentech. So we're going to go look that up. So according to Lentech, 1 mole of sodium azide is 65.01 grams. Make sure that you can get that number too. And then down here, 1 mole of nitrogen is 28.01. Excuse me. All right, so let's take our 20 grams of sodium azide, and we'll do the dimensional analysis here. So we'll turn grams of sodium azide into moles, so that those cancel out. Then we're going to turn moles of sodium azide into moles of N2. Like that. And then finally, moles of N2 into grams of N2. Like that. I ran out of space, unfortunately. So that's the unit that's left over, this grams of N2. So that's going to be the units of my answer. So now I can just fill in the numbers. So 1 mole of sodium azide is 65.01 grams. 1 mole of sodium azide, 65.01 grams. 2 moles NaN3, 3 moles N2. 2 moles NaN3, 3 moles N2. And then finally, 1 mole of N2, 28.01 grams. 1 mole N2, 28.01 grams. Now we put it all in the calculator. What do you get? 20 times 3 times 28.01 over 65.01 times 2. I got 12.9 grams of N2. So that's what we did to solve this problem. We started with a quantity of grams. I turned that into moles. I then turned the moles of NaN3 into moles of N2, and I turned those moles into grams. All right, so now I want you to try this problem. We're going to do a micro experiment with sodium azide, and we're going to use this many grams, which is a tiny number. How many molecules of nitrogen do you make? There's the balanced equation. Now, instead of turning something from moles into grams, for this one you'll need to go in a different direction. You'll need to use a different number. So I'd like you to try that to see if you remember what to do from Unit 14. Or 13, actually. Okay, so give this a shot. We'll go over the answers in just a bit. And then after that, I think we'll take our break. All right, 2 more minutes. We'll go over the answer. All right, let's go over the answer here. So I need to include the number. All right, so we're using a teeny tiny amount of sodium azide here. But we are still starting with the mass of sodium azide. And we want to find out how many molecules of N2 are made. So first we'll turn everything into moles. And then we'll use the mole to mole ratio to connect these two. So let's go and figure out the relationship. So first, the mole to mole ratio for this is 2 moles NaN3 is 3 moles of N2. And that hasn't changed because it's the same equation, yeah? Then to do grams to moles, well, this is the same as before. 1 mole of NaN3 is some number of grams that I don't have anymore because I cleared the page. So NaN3, 65.01, that's right. And then down here, in a mole of anything, how many molecules are there? Well, it's Avogadro's number, right? And now we're all set, so now we can do the problem. So I'm going to use this tiny amount, 1.82 times 10 to the minus 6 grams. Doesn't matter that it's small. We do the problem exactly the same way. So we'll go grams, NaN3, so that these cancel out. Moles of NaN3. And then we'll do moles of NaN3 to moles of N2. Cancel those out. And then we'll do moles of N2 to molecules of N2. We'll cancel those out too. And so that's going to give us just molecules of N2 because that's all that's left over for our units, right? Okay, cool. Let's do the numbers. So I got 1 mole NaN3, 65.01 grams. 1 mole, 65.01 grams. 2 moles NaN3, 3 moles N2. 2 moles NaN3, 3 moles N2. 1 mole of N2 is Avogadro's number of molecules. 1 mole, Avogadro's molecules. There you go. Make sure you get the numbers in the right spot. And we'll punch it on the calculator, and we should get... It should still be a large number. Even though the mass is tiny, Avogadro's number is just so humongous. And I got 2.53 times 10 to the 16. Don't forget the times 10 to the 16 part. That's important. If you report that there are only 2.53 molecules made, those are some of the biggest molecules you'll have ever calculated. Let me just get that out of the way there. All right, that's how you do that problem. And we'll just scroll right through these two. There you go. So when we come back, we'll do another few problems where you have to actually balance the equation yourself. So we'll do that after the break. Let me put the timer up here. I'll actually start the timer today. Yesterday I didn't start the timer. Had to edit that midway through. And we'll get some more music going. So see you in a bit for that. away again. I didn't realize that the track I had clicked on was like 17 minutes long, so... Normally I sit here and curate the music as it's playing during the break, but I got up to get water and then pet the cat. And I sat back down and I was like, wow, this song is still playing? I have a whole playlist queued. Oops. Oh well. I like that song anyway. Alright, so here's what we're going to do for the next problem. So now you're going to have to do all the work on your own to get to the answer here. So we're going to put 5 grams of nitrogen in a container with excess hydrogen to produce ammonia. But I don't give you a balanced equation. So first of all, you need to write the equation based on what you see here. Balance the equation, and then do the stoichiometry with 5 grams of nitrogen. So first write out the equation. Once you got the equation, type it in the chat, and I'll verify whether it's correct or not. And then do the calculation with the 5 grams, okay? So give this a shot. We'll go over the answers in a little bit. Oops, I hit the button on accident. All right, so it looks like we have the right formula. Some answers are coming in, so 2 or 3 more minutes or so, and then we'll go over the answers to this problem. All right, let's go over the answer. So first we got to write the balanced equation. So I'm going to react N2 and H2 to make NH3. And I'll actually do it this way so that you can see the... So first I'm going to multiply this side by 2. So I get that. And then I'm going to multiply this by 3 to get the equation. Oops, sorry, 2 times 3 is not 3. There you go. So there's our balanced equation, so that's all good and all. Let's clear out this. And then we'll do the problem. So now I need to do grams of ammonia. Oops, sorry, not grams of ammonia. We're doing grams of N2. And our goal is to figure out how much ammonia we make. So we'll turn everything into moles. And then we'll turn those two things into each other. The ratio for moles of N2 to moles of NH3, there we go, is 2 NH3 to 1 N2. So 1 N2, 2 NH3. There we go. And then the other two I got to go to Lentech for, so let me go find that. Where did I put it? There it is. NH3 is 17.03. So And then 1 mole N2 is 28.02. Okay, so let's do the problem now. So 5 grams of N2, grams of N2, moles of N2. We'll cancel those out. And then moles of N2 will turn into moles of NH3. Just following along our diagram here as we do this. Moles will become grams. And then the answer will be in grams because that's the last unit we have. And now we'll do the numbers. So 1 mole is 28.02 grams of N2. 1 mole, 28.02. 1 mole N2 is 2 moles NH3. 1 mole N2, 2 moles NH3. And then 1 mole NH3 is 17.03 grams. 1 mole, 17.03 grams. We'll punch in the numbers into the calculator. And I got 6.08. There you go. All right, if you have any questions about how we did that, let me know. All right. So there are more practice exercises to do here. I have a feeling that we could probably do these on our own. So I'm going to leave these exercises for you to try later on. And if you have questions about them and you want to know the answer, I can do the problem really quickly and send you the answer and post it on Discord or whatever. But we are going to get more practice because now what we're going to do is we're going to apply a concept called the limiting reactant. So in the previous reactions, we were always saying excess. And what that meant was I am using up as much of this other reactant as I need because I have plenty of it. I'm not going to put a specific amount in the container. I have infinite. That's convenient for making the problem simple because then we can solve the problem based on just one number. But reality is not that simple. And so what we need to do is consider that both reactants could be present with a certain amount of mass, and one of them is going to run out, and the reaction stops after that point. So, for example, let's suppose that I have this formula here. So, I'm going to make a cheeseburger, and I'm going to use the cheeseburger reaction to make a cheeseburger. So, here's what we're going to do. So every reaction requires 2 patties. So, there's my patties. You know, I'm not going to do this in different colors. What am I thinking? Every reaction requires a bun. And then I have to have cheese. And that will get me my cheeseburger. That looks terrible. I'm not an artist, but you get the point, right? All right. Now let's suppose that I make burgers as fast as I can with the things that are available. And so I have this much cheese. And I have this many buns. And I have this many patties. Yeah, it looks like Saturn, right? All right. So I'm going to make a burger out of these. So I can make a burger, I need 2 patties, a bun, and a cheese. So I'm going to just start counting them off. Oops, if I can get the right color. Okay, so 2 patties, bun, cheese, burger. 2 patties, bun, cheese, burger. 2 patties, bun, cheese, burger. And now when I get to this next part, it's like, uh-oh, I can't make any more burgers. I ran out of buns. I have plenty of patties and cheese left to make another burger, but I can't make any more buns. So I am limited to making only these 3 burgers. These reactants will remain unused. And the thing that I ran out of is known as the limiting reactant. That should be an I, but it kind of goofed there. There we go. Limiting. There we go. Now, with reactions, this is going to be the exact same premise. If I use up my contents one molecule at a time, eventually I do run out of molecules for one reagent, and the others will still be abundant. The one I run out of first is the limiting reactant. Now, how do we show this mathematically? So let's suppose that I have these quantities. What would I run out of first just by looking at these numbers? Well, here's how we would calculate it. So I can do 10 patties, and I know that to make one burger makes 2 patties. So I can make 5 burgers with this. If I do that with buns, I have enough buns to make 6 burgers. And if I have cheese, I can make this many burgers. So this is the amount of product that I can make when I look at each substance on an individual basis. And you'll notice that, oh, we basically did the problem once for every reactant that was involved. And that's what you're going to do. You're going to do the problem most of the way through for each reactant you're given. And then at the end of the problem, you choose the answer that is the smallest, because this was the limiting reactant. And so the number of burgers that were made from this reaction was 5, because I ran out of meat. I have extra buns and extra cheese, but I don't have enough meat. Somebody needs to go to the store and get more. All right. So again, we're going to look for the limiting reactant when we do these problems. And once you identify the limiting reactant, that's your answer. You circle that number. The other numbers get crossed out. We did not make 6 or 8 burgers. We only made 5. So let's suppose that I'm doing a reaction to make water out of hydrogen and oxygen. So these reactions, as shown, show how that happens. But let's suppose that I had a mass in there. So instead of 2 moles of hydrogen, I actually had, oops, I guess it would be 4 grams. And then 1 mole of oxygen would be 32 grams of oxygen. I should make 36 grams of H2O. Because of the conservation of mass, right? So if I had these amounts, they would add up to be pretty much exact. I'm doing this to like 1 or 2 sig figs, but that's good enough. But now let's suppose that instead of having 4 grams of hydrogen, I actually had 8. I only really need 4 grams to do the reaction with my 32 grams of oxygen. So when I am done with the reaction and everything has happened, all of this gets used up to go get put in here. And then the 4 grams that I needed also got used up, which leaves 4 grams in the container. So after the reaction would occur, I would have this excess. And I would have the 36 grams of water that I expected. So whenever we are doing calculations, we want to look at only the one that runs out first. How do we determine which one runs out first? Well, you just convert that to moles, and then turn that into moles of a product. And whichever one makes less product must have run out first. So let's do an example. All right. And that's basically what I said here. So let's do an example of this process. So do I have a balanced equation here? I do. Okay. We're going to react 40 grams of methanol with 46 grams of O2. How much CO2 is made, and which one runs out first? So you can make the chart over here if you'd like to show how the dimensional analysis works. I'm going to assume that we can do that by now. I'm going to write out our starting amounts. So this is methanol. And I have 46 grams of O2. Now the question is asking me, what is the mass of CO2 produced? So I want to convert these to CO2. So whenever I have grams of something, I got to turn it into moles first. So we'll do grams of methanol to moles of methanol. And then we'll do moles of methanol to moles of CO2. And then finally, we'll do moles of CO2 to mass of CO2. And all these units cancel out that I forgot to do. And so now we'll just go to Lentech and fill in the numbers for the balanced chemical equation right here. So moles of CO2 and moles of methanol, looks like we make 2 CO2s per 2 methanol, according to the equation that's up above here. And then grams per mole, so I know CO2 is 44.01. I don't know methanol, though. We'll go to Lentech for that. CH3OH, 32.04. Okay, so 40 grams of methanol can eventually make how much CO2? So let's find out. 40 times 44.01. So these 2's just kind of cancel out, right? We don't need to worry about them. So I got 54.9. Okay, now let's do the same calculation with oxygen. So we'll turn grams into moles. We'll turn moles of O2 into moles CO2. We'll turn moles CO2 into moles. Oops, not moles, I'm sorry. Grams of CO2. Get all my units cancel out. Look at that. And then we'll just fill in the numbers again. So 2 moles of CO2 from 3 moles of O2, so that one's good. This is 32.00, and this is still 44.01. So times all this together. And when I do this, I get 42.2 grams CO2. All right, so having done the problem twice, if I put in 40 grams of methanol, I could potentially make 54.9 grams of CO2. But if I put in 46 grams of oxygen, I can potentially make only 42 grams of CO2. Since I have made less CO2 with oxygen, oxygen is the limiting reactant. It limits the maximum amount that I can make. So any of the extra that I would have made up here comes from the excess methanol that would be left over after I ran out of oxygen. Now, when you do these types of problems, it helps to identify what is your limiting reactant and what's your excess. Now, when I say excess, I don't literally mean the letters X and S. I mean excesses and you have a bunch of it. This. But I just write XS because it's 2 letters. It's just like I wrote for LR, so it fits the theme. What do you do with the excess calculation? This is what you do. Woo! You draw a big scribble through it because it's not a number that will help you solve the problem. Now, it may be useful information for a later problem, so what I would recommend is that you do a loose scribble and don't do something like, say, this. Woo! And obliterate the answer or erase it or whatever. Because if you need that information, now you have to do the problem again. So undo that. Now I gotta get my old brush back. There we go. So I just draw a loose scribble through the calculation so you can still see what's under it. Because maybe the next problem would ask you, how much more CO2 could you have made if the other reactant was the limiting reactant or something? And then you would need this number right here. So never completely erase or obliterate anything in terms of a calculation, because you might need it later for some reason. When you get to graduate level work, or even like when we go back to face-to-face teaching and you start taking labs in person with me or another instructor, when you're keeping all your records in the lab notebook, you can't cross anything out permanently. You could just draw a line through it and then right next to it. And that's the custom, I guess we would say. When you get to graduate school, your work is actually the property of the university you're working for. And if you obliterate your work, that can be criminal if the information that you are deleting is sensitive. So just be mindful of that. So get into the habit of not just crossing everything out and scribbling it to death, because I know a lot of people, I was like this too. You make a mistake and, oh, I'm embarrassed, I made a mistake, and you spend 5 minutes crossing out a problem. Don't do that. Just draw a line through it. Lessons for life from Chem 140. Now, you'll notice in this slide, I stopped at moles. Well, that's interesting. Can I go back and do that? Can I just stop at moles instead of doing the whole problem through? And the answer is, yeah, absolutely. So now I have to actually go back and do... It's not going to let me because for some reason this version of Photoshop breaks the history when I'm on the tablet. So Now what I need to do is we're going to do this. We're going to stop the problem at this part. We're going to get rid of these. We're going to go boop. That didn't quite work. Boop. There we go. And we're going to say, okay, what if we had just figured out how many moles of CO2 were made? Because the number of grams of CO2 is related to the number of moles of CO2, right? And the answer is, yeah, it absolutely is. So 40 grams of methanol would make 1.25 moles of CO2, and 46 grams of oxygen would make 0.958 moles of CO2. This is still lower, so it's still the limiting reactant. And then I could use this to figure out grams of CO2, which we just did. So when you do these problems, you have several ways to do them. The first way that I showed you was to just solve the problem all the way through, and then pick the number that's smaller. That's the limiting reactant. Excuse me. Or if you just wanted to go to moles of the product and save yourself one step of the calculation, you could do that too. It's faster to just go to moles of the product and then turn the correct one into grams. That'll save you one step. But for some students, it's just more intuitive. Oh, I'll just do the problem twice and pick the smaller number. That's the limiting reactant. If that helps you do that. All right, so let's have you try one on your own. So I'm going to give you these phosphorus fluoride compounds. We're going to react them with fluorine. I'm going to give you 100 grams of PF3 and 50 grams of F2. What's the limiting reactant and how much PF5 is made as a result? So, is the reaction balanced? First of all, you should check that. And without doing much, you should probably come to the conclusion that, yeah, it's balanced. I just add the 3s and the 2s together to get 5. So that's fine. And now that you've checked that your equation is balanced, because you should always check, make sure, do the stoichiometry with both of the reactants and see which one's the limiting reactant. Give you 5 minutes and we'll go over the answers in a bit. All right, one more minute, we'll go over the answer. There you go. Sorry about that. I was trying to do something in Photoshop to make it a little easier to see. You can't see the overlays that I have, but I have like extra buttons on my screen that are sort of over where I'm drawing. And I moved one of those and I totally broke the formatting. So I had to replace it. And that took a second. All right, so we're going to work with 100 grams of PF3 and 50 grams of PF2. Not PF2, sorry, F2. So we'll turn grams of PF3 into moles of PF3. And then we'll turn moles of PF3 into the product that we want. So that cancels and that cancels. So this is 1 to 1 because all the coefficients are 1. And then I got to look up the molar mass of PF3. That's on Lentech, 87.97. So the number of moles of PF5 I could make from that mass of PF3, 1.14. Or sorry, 1.137, since I get 4 sig figs. All right, we'll do the same thing for F2. So grams will turn into moles, and then I can do moles of F2 and moles of our desired product. All right, 1 to 1 ratio here. Grams to moles of F2. I gotta look that up. I think it's 38. Oh, it's exactly 38. Well, 38 to 2 decimal places. I get that many moles. Who's the limiting reactant? PF5 is. This one's excess. Woo! We don't use the excess one. So then we'll just take this number and we'll make grams out of it. So 1 mole of PF5 is 125.97 grams. And the answer I get is 143.2. There you go. Now, could you have turned both of these to grams and selected the smallest number? Yeah, and it would have been this one. And that would have been this number right here. So again, use whichever method you find easier to do. All right, that's all the time that we have for today. Next week, when we return, we are going to be finishing up this chapter. So we'll do the rest of the limiting reactant practice on Tuesday. We'll do percent yield, and then we'll start Unit 15, or I'm sorry, Unit 16, which is the last unit, actually. And we'll do a little bit more of that on Wednesday when we talk about the lab, because we're going to need to in order... We'll have to have part of that discussion. And then on Thursday, we'll finish up any Unit 16 that we haven't finished. And we'll talk about what happens after that. Like, it's just quizzes and exams and stuff like that past that point. So we're really close to the end. Just 1.5 more chapters left. So hang in there. Make sure you are keeping on top of the quizzes because a bunch of them are coming up and are due. One of those quizzes is due tomorrow, so make sure that you get that done. Don't forget the others. And also, oh, that should say lab worksheet number 4. I'm just realizing. Look at that. I've had the wrong announcement up. Oh, there we go. Yeah, party for last class. You all can send me pizza. I mean, I'm perfectly fine if you want to, like, mail me food. That sounds delicious. All right, have a wonderful weekend. Get some sun if it's out there. And take care. See you next week.